So we extend our knowledge. If this electric field E and this electron, the free charge, they both are in the conductor. Conductors are made like of copper or aluminum or gold or silver, right? So what happens? And we concluded that this electron will always move against electric field, in opposite direction to the electric field. And this electric field was created by this potential difference. And that movement of electron, this electron, when it moves against the electric field, gets its kinetic energy, right? So and the kinetic energy of the electron is the electron charge itself into the product Va minus Vb, the potential difference actually. Okay, so kinetic energy is the electron into the potential difference. So this is what we saw previously, and this is our key question to analyze further when this electron is moving. And then you remember we took few examples, like the electron is moving against the electric field, and in the path the electron may collide. In the path the electron may collide with many things, okay, may collide with many other obstacles. Remember, in actual, the nucleus is very tiny little region. However, the electron cloud is much bigger in size. So electron can take a lot of space. So the electron cloud has huge space in comparison to the this little nucleus, right? So in reality, inside the conductor, inside the conductor, when the electron makes a collision, then it scatters. Remember, this nucleus was tiny little, but a huge orbiting electron cloud. Huge orbiting electron cloud. So a collision of electron with the electron cloud even will scatter the electron. Okay. So say this red electron, this one is moving this way, right? And as I said, uh, the nucleus is very, very small in size. The nucleus is very tiny little thing, right? However, the electron cloud around it is huge, right? So when the electron makes a collision, it may get scattered. And when it finds a vacant space again, it will again try to move against the electric field, this electron. Okay, so inside the metal there's a huge vacant space. Why? Because those nuclei are very, very tiny, and the electron cloud, which is a vacant space, is huge in size, right? So in metals we have huge vacant spaces through which the electrons move around. Okay, so then we also concluded that when electron moves in a certain direction, it constitutes your magnetic field. The electron moves in a certain direction, it constitutes a magnetic field. And also we concluded that if we have one atom like hydrogen, this huge orbiting electron cloud around it. Okay, so a hydrogen atom is a very powerful magnet in that context. But we also concluded that the hydrogen atom doesn't like to exist in the atomic form. It will always try to make a bond with another hydrogen. Okay, so one hydrogen here will make a bond with another hydrogen atom, and the two will always make a bond if their spin is precisely opposite to each other, or when they find the condition that the electron spin in both hydrogen atoms precisely opposite to each other. Only then they make a hydrogen molecule. And once they make a hydrogen molecule, due to the opposite electron spin, their magnetic moments are opposite to each other, effectively cancelling each other and resulting in a very, very inert or very, a molecule with very, very low magnetism. So hydrogen molecule, in fact, is exhibiting very, very low magnetism. It's called as diamagnetic. So hydrogen, as per Bohr's, in all atoms, we have electrons moving around with tremendous speed. So they all are basically magnets. But remember, sometimes they make molecules, and they make molecules where the electronic spin is opposite to each other, effectively canceling the magnetism of each other. And this is the story, right? And but but one day Einstein said there's no magnetism in this universe, right? He concluded that the magnetic field, which is known to humans for centuries, is actually again the electric field. Okay, so as per Einstein, and he proved that in his special theory of relativity, that a magnetic field does not exist, and it is again the electric field. And how it is the electric field, we saw that if we have this positive positive nucleus and this negative electron, they have straight lines of the electric field is always a straight line, right, this way. But the problem with the straight line of this electric field, that the two straight lines cannot cross each other. So if, say, this is the electric field of an electron, suppose. So the two straight lines cannot cross each other actually. So what happens? See, the two lines, they move this way. Okay, they move this way, right? Okay, they move, they cannot cross each other, so they move in. So there's a little change in the path of the electric field. So now when inside a conductor there are nuclei, inside a conductor there are nuclei, there are electrons which are moving, and there's a third electric field, the green electric field, because of the voltage. So if in a conductor we have this voltage, and because of this voltage we have this electric field, and then we have the positive charges. So when the electron moves against this electric field, this electron is moving against this electric field, the electric field of the electron is no more a straight line, right? Because of the interaction of the electric field of the electron with the electric field of the nucleus and the electric field of the battery. Because of their interaction, see, the electron electric field may like to come down like this, may like to come down like this. Okay, but because there's a green electric field because of the battery, and the two cannot cross each other, so it effectively changes its direction. Okay, so inside a metal, or inside a metal wire, the electric fields of the moving electrons are no more straight lines, and those zigzag or disturbed electric fields of the electrons, as per the Einstein's theory of special theory of relativity, they are called as the magnetic field. तो आइंस्टाइन ने ये कहा था कि ये जो डिटीरिएटेड इलेक्ट्रिक फील्ड है इलेक्ट्रॉन्स की, इसको सदियों से साइंसदान मैग्नेटिक फील्ड का नाम दे रहे थे। हालांकि ये मैग्नेटिक फील्ड जेनेरिकली नहीं है, ये अगेन हमारे पास इलेक्ट्रिक फील्ड ही है, उसकी एक डिफरेंट शेप है, बिकॉज ऑफ द रिलेटिविटी, because inside the metal there are statically held positive charges. They are not moving around. Those positive charges are actually not moving around. They are static. So their electric field are straight lines. They try to be straight lines. But remember, uh, they they sometimes they sometimes try, they may cross another electric field, which is because of this green voltage battery, this green electric field. So the electric field cannot cross. The electric field cannot cross. So what happens if the electric field cannot cross? The electric field will change their direction, and because of those change and deterioration in the electric field inside the conductor, you end up on electric field which is not a straight line, and people for centuries call this phenomena as the magnetism. तो आइंस्टाइन ने कहा कि एक्चुअली ये जेनेरिकली मैग्नेटिक फील्ड नहीं है, ये हमारे पास अगेन क्या है, इलेक्ट्रिक फील्ड ही है, और उसकी एक डिफरेंट शेप है. सो there was a theory about all these things, and we were moving through this theory to find out the flow of electron and what kind of electric field it is going to cause. If the electron moves, if the electron is static, what's the electric field shape? If the electron moves, what happens to the electric field and how you get the magnetic field. आइंस्टाइन ने कहा था खैर है, आप कोई इशू नहीं है अगर आप इस इलेक्ट्रिक फील्ड की relative फॉर्म को अगर आप मैग्नेटिक फील्ड का नाम दे रहे हो तो नो इशू इन दैट, बट जेनेरिकली स्पीकिंग दुनिया में मैग्नेटिक फील्ड का वजूद नहीं है. और उस पर क्वेश्चन भी काफ़ी साइंसदानों ने किए थे कि ज़मीन का मैग्नेटिक फील्ड कहाँ से आया, सो ही एक्सप्लेन दैट ऑल्सो. तो हम तो हमारे पास जब भी इलेक्ट्रिक फील्ड होगा, इलेक्ट्रॉन ने हमेशा उसके अगेंस्ट मूव करना है. और यही फिनोमिना, दिस वेरी सिंपल कॉन्सेप्ट हियर is making the entire basis of radiation from the metal. If you have a metal in two pieces, if you have a metal in two pieces, that metal can radiate electric field if the electron is moving, if the electron is moving upward. Okay, if suppose a potential difference is applied here for this half, the electron is the electron in the structure is trying to make this path of movement, and again the electron here will try to make this path of movement through this entire circuit, right, where you apply your voltage source, right, and through the other half of the voltage cycle, through the other half of the voltage cycle, the electron will try to go downward in the other direction, right. So the electron will go in the other direction, and effectively um, when this happens, you get you get the electric field, which is radiated in some shape, which is that electric field is radiated in some shape, right. So we have already gone through this little concept, and we'll be expanding this concept of radiation in more detail in our next chapter when we realistically understand how the electron is moving around, how it vibrates if things are time varying, how it moves from one point to another point if things are not time varying, if they are static or DC. The electron really moves from one point to another point along the line. But if it is time varying voltage, the electron vibrates along the line. So when we fully explore this concept, and then inside a conductor, when we fully explain the phenomena of electric field and the magnetic field, the electromagnetism, then we will be in the position to really explain this radiation mechanism. So, so effectively, what's the basis is that whenever we have electric field, suppose in this direction, the electron will always move against it. And in the process, the electron is going to get its kinetic energy, which is known to us and is half mv square. However, this m is the mass of the electron, but I will put star here because this electron typically moves in a conductor, right? So in the conductor, the mass of the electron is little bit higher than its free space mass. So the mass of the electron is little bit higher than the its actual value 9.11 into 10 to power minus 31 kg. It's little bit higher mm, uh, than the actual mass of the electron in the free space. So this kinetic energy is basically the work done, right? The work done, this kinetic energy is basically the work done by this battery, right? Work done by this battery source, right? Uh, the voltage source. So I will put this equation uh, as the electron charge into, if say here we have the potential VA on this positive plate, here we have the potential difference VB on this other plate, we have VA minus VB. So this is the amount of work or the kinetic energy the electron will be gaining inside the conductor. And when this electron moves inside the conductor, it faces many collisions, which we explained previously, and we modeled we modeled those collisions. We make an equation of those collisions as the resistance of the material. Okay, so those collisions of the electrons, they make the resistance of the structure or the wire or the material. Okay, so in the process, when this electron was moving, it makes collision, and we define the scattering. We defined the scattering time. Scattering time was the time between two collisions which the electron faces. So we denote it by the symbol tau. And we also said it's in the range of 10 to the power minus 14 seconds for copper. Sometimes little less, sometimes little more than this value, because variations in the temperature and all those sort of things, the collision may be different. But the scattering time was really going to define us the drift velocity, which we explained here, right? So that was the drift velocity which on which we were working. Okay, here when the electron makes a collision, it scatters, it restarts its journey from zero velocity. Again, it may face another collision. So the time taken by the electron between two successive collisions was called as scattering time. And this scattering time was really helping us in modeling our resistance value. Okay, so this scattering time is 10 to power, is just typical in the copper conductor. Okay, so the process continued, and in the process, we use the Coulombic force. We use the concept of the Coulombic force and the acceleration of the electron in the metal, and we produce a new shape for the Ohm's law. And we said that this equation is really relating the uh, current J, current density. This was the current density, right? It was relating this thing to the electric field. This E is the electric field intensity. And again, as I said, it's a very tricky question. Why? Because it is going to relate something which is physical. See, J is very much a physical thing. Say this is our conductor. Just for example, this one is our conductor. And suppose this is some cross-sectional area of the conductor. So these electrons are moving through it. So if say this is our cross-sectional area A, and the electrons are moving. So say three electrons moved, right? Three electrons moved. Now on this part of the wire, on the B side of the wire, the electrons has deficiency, and those three electrons really move to the A side of the conductor. So in remember, this happens in DC. If you have the DC voltage source, okay, this always happens in the DC case. If you have a DC voltage source, this will happen. If this electron again moves to the A part, so see, electrons in quantity are rising in A, and electrons in quantity are decaying in section B of the conductor. So this is really the rate of change of electrons, right? It's really rate of change of electrons, rate of change of charges. So a rate of change of, I would say, the quantity, the number of electrons, right? Charge, Q, electronic charge. So electronic charge is decaying on in section B of the conductor. So I'll put a negative sign here because it's a decaying, it's a negative slope. Because since, see, we know that if say this is my time, the time axis, and say this is the vertical axis is going to be my charge. So this negative means this decay, right? Okay. So you can relate different numbers here on this graph, okay? You can go through some calculus to define this decay function. So this decay is really minus dQe divided by dt. Okay. On the other hand, on the right side of the conductor, on this right side of the conductor, electrons are increasing in quantity. Electrons are increasing in quantity. So here dQe divided by dt is positive. So on the right side of the conductor, really the electrons are increasing. On the left side, so I will call this is region A, and the other one was a region. This decay is in region B. Okay, so decay is in region B, and the rise is in. And remember, see, if 3 electrons are decayed in region B, 3 electrons are raised in uh, region A. So really, the two equations are equivalent, and this is called as continuity. This equivalency in the positive slope and in the negative slope. See, this gray is a negative slope, this green is a positive slope. So this equivalency in the positive slope and negative slope is called as continuity. But remember, it is known to us as the current. So we will call this as the current continuity. U I T, continuity, current continuity equation, right? Current continuity equation. So this is really going to happen. And remember, we call this as a kind of Ohm's law, because why? See, this J is current, this sigma is the reciprocal, this is conductivity. This conductivity, and conductivity is the reciprocal of resistivity. So it's really the current thing here, and the conductivity, and the, see, the electric field intensity. The electric field intensity is going to cause the voltage. E equals to V divided by D. So it's going to cause the voltage. So it's really another form of the Ohm's law. Why much better forms of the Ohm's law? Because it considers this conductivity thing. Okay, and the conductivity sigma, sigma is this conductivity is number of electrons which are moving from left to right, um, charge on one electron, charge on one electron, and charge on one electron again facing some tau, the scattering time, moving with some mass. The mass is m star, little bit higher than the actual mass. So this thing is really making the conductivity of the material. Okay, so all these things combine together, and they make a constant which is called as conductivity. And based on this constant conductivity, remember this conductivity is a constant thing. Based on this, um, based on this, we define, we basically classify materials, right? Uh, this conductivity is, uh, say if I take the 1 meter cube of copper, 1 meter cube of copper, I will find 10 to the power 29 free electrons in 1 meter cube of copper. So if I take a volume of 1 meter cube of copper, there would be 10 to the power 29 free electrons. It's like 10 to the power 29 free electrons are like 100 billion of a billion of a billion. So it's a huge quantity. So in a certain conductor, suppose this one, in a certain conductors, for this one, the number of free charges, the number of free charges and charge on one electron, and then again QE and the scattering time divided by the effective mass of the electron. Okay, this parameter is called as conductivity. And Rj is really the conductivity, which is a constant thing to the electric field. So this equation is really going to give us the relationship between electric field, which is coming from the voltage divided by D, and this is current divided by area. Okay, so again, see this current is flow of electron. I is dq by dt. So this is a physical thing. It has a mass. The charge has a mass. It's a physical thing. However, this E is a field phenomena. So very interesting equation. Very interesting equation is going to relate something which is physical, has a mass to something which is non-physical, is a field phenomena. But remember about this conductivity. If you raise the number of free charges in a material per length per square meter, uh, conductivity will raise. Okay. Of course, this is a constant. This thing is a constant. This thing is a constant. This thing is a constant. Okay. So no issue with that. If scattering time is raised, uh, conductivity will further raise. So if you increase the scattering time, uh, if suppose scattering time is increased, conductivity will increase. So scattering time is the time between two successive collisions. This also means if there are less collisions for the same speed, if there are less collisions for the same speed, you will have more conductivity. See, rate of change of charge is going to give us the speed of the electron somehow. We'll see that. Okay, we'll see that equation. The rate of change of charge is going to give us the speed of the electron, the velocity of the electron. We'll see the equation. So if the scattering time is more, this means less collisions. Okay, is this clear? More scattering time means what? More scattering time means what?
Yes, sir, clear.
Yeah, yes.
Less, more connectivity.
Yes, yes, exactly. Less collisions. And remember, if this one is raised, if the effective mass of the electron is raised, that will do what? That will lower the conductivity.
Decrease in conductivity.
हाँ, तो मटेरियल जितना ज्यादा डेंसर होगा, ठीक है, मटेरियल में जितने ब्लैंक स्पेसेस कम होंगे, इलेक्ट्रॉन का मास ज्यादा फील होगा. और कंडक्टिविटी रिड्यूस होगी। देखें, ये फॉर एग्जांपल हमारे पास एक कंडक्टर है, ठीक है। अगेन मैं इसकी डायग्राम ड्रॉ करने की कोशिश करता हूँ। ये हमारे पास एक कंडक्टर है, राइट। जैसे कि आपको मैंने बताया कि बहुत ही छोटा सा न्यूक्लियस होता है और बहुत बड़ा इलेक्ट्रॉन क्लाउड होता है जिसमें इलेक्ट्रॉन मूव अराउंड करते हैं, राइट। यहाँ पे इलेक्ट्रॉन्स मूव अराउंड करते हैं, राइट। सो इलेक्ट्रॉन्स क्योंकि मूव करते, सो सी दिस इज द न्यूक्लियस इज अ फिल्ड स्पेस। न्यूक्लियस एक भरी हुई जगह है, फिल्ड स्पेस। हाउएवर द इलेक्ट्रॉन क्लाउड इज अ वेकेंट स्पेस, ठीक है। तो चूंकि इलेक्ट्रॉन क्लाउड बहुत ज्यादा बड़ा होता है तो हमारे पास मटेरियल में बहुत ज्यादा ओपन स्पेस होती है। जब ज्यादा ओपन स्पेस होगी, एम स्टार स्मॉलर एंड स्मॉलर एंड स्मॉलर होगा, दिस वन। लेकिन अगर कॉम्पैक्ट होगा, अगर इलेक्ट्रॉन क्लाउड इज स्मॉलर, द इलेक्ट्रॉन क्लाउड इज स्मॉलर, ठीक है। अगर इलेक्ट्रॉन क्लाउड स्मॉलर है तो वैकेंट स्पेसेस कम होंगे ना, फौरन ही अगला न्यूक्लियस स्टार्ट हो जाएगा, फौरन ही अगले न्यूक्लियस की स्पेस स्टार्ट हो जाएगी ना। तो वैकेंट स्पेसेस कम होंगे, तो क्या होगा, जब वैकेंट स्पेसेस कम होंगे तो इलेक्ट्रॉन का इफेक्टिव मास ज्यादा फील होगा और कंडक्टिविटी रिड्यूस हो जाएगी, तो इलेक्ट्रॉन के कोलिजन्स बढ़ जाएंगे। ओके। ऑल्सो ये जो टॉ है, इट ऑल्सो डिपेंड्स ऑन टेम्परेचर ऑल्सो। ओके, टेम्परेचर में वेरिएशन से इस टॉ में वेरिएशन आती है, सो इट ऑल्सो डिपेंड्स ऑन टेम्परेचर। ओके, ओके, समझ आ रही है बात की, समझ आ रही है बात
यस
की।
सर, समझ आ रहा है।
ओके, ओके। सो सो ना एक छोटी सी एग्जांपल लेते हैं जिसमें रियली हमारे पास एक कंडक्टर होगा और उस कंडक्टर में हम जब वोल्टेज अप्लाई करेंगे, ठीक है, वोल्टेज अप्लाई करेंगे तो देखिए बैटरी बैटरी वोल्टेज हमेशा आपको पता ही है डीसी है, तो क्या बनेगा, इलेक्ट्रिक फील्ड अंदर बनेगा, ठीक है। और इलेक्ट्रॉन्स क्या करेंगे, इलेक्ट्रॉन्स जो है इस इलेक्ट्रिक फील्ड को रिस्पॉन्ड करेंगे और इलेक्ट्रॉन्स इस इलेक्ट्रिक फील्ड के अगेंस्ट मूव करेंगे। तब तक इलेक्ट्रॉन्स मूव करते जाएंगे जब तक इलेक्ट्रिक फील्ड खत्म ना हो जाए। ये हमें ऑलरेडी सब कुछ पता है कि इलेक्ट्रॉन्स क्यों पसंद नहीं करता इस इलेक्ट्रिक फील्ड को। तो जैसे ही इलेक्ट्रिक फील्ड आएगा, इलेक्ट्रॉन इसके अगेंस्ट जाएंगे और इस इलेक्ट्रिक फील्ड को ख़त्म करने की कोशिश करेंगे। तो ख़त्म कैसे होगा, बेसिकली इलेक्ट्रॉन की काइनेटिक एनर्जी बनेगी जो कि वी एम माइनस वी बी होगी और वो इस इलेक्ट्रिक फील्ड से वो एनर्जी आनी है, राइट। सो इसको हम क्या कहते हैं, इस रीजन को हम इलेक्ट्रॉन का कंडक्टर का क्रॉस सेक्शनल एरिया ए कहते हैं, ठीक है। तो जो इलेक्ट्रॉन इस क्रॉस सेक्शनल एरिया ए से पास होते हैं, जितना करंट इस क्रॉस सेक्शनल एरिया ए से पास होगा, उस करंट आई को एरिया पे डिवाइड करके हमें करंट डेंसिटी मिलती है, विच इज जे। सो एक सर्टन सिचुएशन है, सर्टन कंडक्टर है, सर्टन वायर है जिसमें जे का जो प्रोफाइल है वो क्या बन रहा है, 1/r एक्सपोनेंशियल माइनस टी ए आर एम्पेयर्स पर मीटर स्क्वायर, ठीक है। ये एक सर्टन सिचुएशन बन रही है, ओके। आर क्या है, आर इस वायर का आर क्या है, रेडियस है।
रेडियस है सर।
जी, रेडियस है, आर वायर की रेडियस है, ओके। अच्छा, तो ये एक सर्टेन प्रोफाइल बिल्ड किया गया। हम लेटर ऑन देखेंगे कि प्रोफाइल्स हम कैसे बिल्ड करेंगे। ये जो करंट जो जे की जो प्रोफाइल है, वो हम कैसे बिल्ड करेंगे, हम इसको देखेंगे थ्रू सम एक्सरसाइज। ओके, अच्छा, अब सर्टेन सिचुएशन है जिसमें आप सर्टेन वोल्टेज अप्लाई करते हो, सर्टेन वोल्टेज भी अप्लाई करते हो। ठीक है, तो आपको याद है कि जे की क्या इक्वेशन थी? जे इज इक्वल टू सिग्मा इनटू इलेक्ट्रिक फील्ड। ओके, तो जे क्या था? इट्स करंट डिवाइडेड बाय एरिया विच इक्वल्स टू सिग्मा, और ई क्या है? ई इज द वोल्टेज डिवाइडेड बाय द सेपरेशन, द डिस्टेंस, द सेपरेशन जिसके अक्रॉस आप वोल्टेज देखना चाहते हो। ओके, ठीक, ओके। और करंट क्या चीज है? करंट आई क्या चीज है? इट्स डी क्यू बाई डी टी। ये रेट ऑफ चेंज है, रेट ऑफ चेंज है, किस स्पीड के साथ इलेक्ट्रॉन अपनी पोजीशन चेंज कर रहा है, किस रेट के साथ, किस टाइम के साथ इलेक्ट्रॉन एक पोजीशन से दूसरी पोजीशन की तरफ जाता है। स्पीड है ना बेसिकली, समहाउ इट्स स्पीड। और हमने इनफैक्ट इसको देखा भी था। यू रिमेंबर एफ कूलम वाज इक्वल टू चार्ज of the electron into electric field intensity। ये you remember this, हमने ये देखा था। और ये
Yes, sir.
बेसिक, सो ये कोलम्बिक फोर्स है, रिमेंबर ये कोलम्बिक फोर्स है, ये कोलम्बिक फोर्स है। लेकिन ये हमारे पास इक्वल है न्यूटन फोर्स के ऑल्सो। अगर हम इस मास को इफेक्टिव मास इलेक्ट्रॉन का ले ले तो ए हमारे पास एक्सिलरेशन है। ठीक है, ए हमारे पास क्या है? एक्सिलरेशन है। और एक्सिलरेशन किस चीज के बराबर होता है? एक्सिलरेशन किस चीज के बराबर होता है? वेलोसिटी।
The velocity के derivative.
हाँ, ज्यादा बेहतर यह है कि आई पुट इट रेट ऑफ चेंज ऑफ वेलोसिटी, इफ आई पुट इट दिस वे। ओके, समझ आ रही है?
Yes, sir. Clear.
ओके, ओके, सो एक्सिलरेशन इज रेट ऑफ चेंज ऑफ वेलोसिटी। ओके, सो सी हम समहाउ इस पूरे फिनोमिना को हम वेलोसिटी के टर्म्स में लिखेंगे। ओके, सो जब आप इसको करेंगे कि ये हमारे पास मास है, एक्सीलरेशन डी वी बाई डी टी। ठीक है, तो ये हमारे पास क्या बना? क्यू ई ई इलेक्ट्रिक फील्ड। ये हमारे पास क्या बना? डी बाई डी टी। समझ आ रही है? इज दिस ओके? सो एनीवे, हम इसको कंटिन्यू करेंगे एंड वी विल डिराइव दिस फिनोमेना इन मोर डिटेल। बट कहने का मतलब ये है कि ये एक्सेलरेशन जो है, ये हमें वेलोसिटी देनी है इसने। ठीक है, अच्छा, अब इसमें देखिए, इसमें हमारे पास वेलोसिटी क्या होगी? ड्रिफ्ट वेलोसिटी होगी। ठीक है, ड्रिफ्ट वेलोसिटी, और टाइम कौन सा होगा? स्कैटरिंग टाइम होगा। बात ये समझ आ रही है ना? सो वेलोसिटी किस चीज के
Yes, sir.
बराबर?
समझ आ रही है.
हाँ, तो वेलोसिटी किस चीज के बराबर है? वेलोसिटी किस चीज के बराबर है इस केस में हमारे पास? ड्रिफ्ट वेलोसिटी। ड्रिफ्ट वेलोसिटी कौन सी थी? जब इलेक्ट्रॉन किसी स्ट्रक्चर के साथ कोलाइड होता है, जस्ट बिफोर कोलिजन जो इलेक्ट्रॉन की वेलोसिटी होनी है वो कौन सी वेलोसिटी है? ड्रिफ्ट वेलोसिटी। ओके,
Just
सो
velocity.
या, सो अब देखिए, अब फॉर एग्जांपल इन फर्स्ट केस हमारे पास इलेक्ट्रॉन या जो करंट है, ये जो चार्जेस है जो एक पॉइंट से दूसरे पॉइंट में एक सेकंड में 5 मीटर डिस्टेंस कवर करते हैं। ठीक है, तो करंट कितना बनेगा? अगर एक सेकंड में 5 मीटर डिस्टेंस कवर करते हैं तो आई डिवाइडेड बाय, इसको मैं एस कर देता हूं, सरफेस एरिया, क्रॉस सेक्शनल एरिया, राइट, दैट आई कॉल दिस एज एस। ठीक है, एरिया, क्रॉस सेक्शनल एरिया of conductor, cross-sectional area of the conductor, right? This is also okay. And this is J. So what this means, J is from here, I is J into S. In fact, J dot S, remember, ये J dot S होगा, क्योंकि देखिए ये J dot S होगा, क्योंकि अगर इस एरिया को मैं इलेक्ट्रॉन की डायरेक्शन, सपोज इफ आई एज्यूम दिस एरिया, इफ आई एज्यूम दिस एरिया, सेम एरिया है, ये भी सेम एरिया जैसे प्रीवियस एरिया था, लेकिन अब चूंकि इलेक्ट्रॉन की डायरेक्शन और एरिया की डायरेक्शन में एंगल आ गया ना, तो डॉट प्रोडक्ट का आना यहाँ पे जरूरी है। ठीक है, किसी टाइम पे लेटर ऑन हम ये केस भी देखेंगे और इसका इफेक्ट मैग्नेटिक फील्ड पे देखेंगे। ठीक है, ये जब सिचुएशन होगी तो हमने मैग्नेटिक फील्ड के ऊपर इसका इफेक्ट देखना है। ठीक है, विल सी दैट लेटर ऑन इन चैप्टर नंबर 8। ओके, सो आई इज इक्वल टू जे एस, और जे हमारे पास क्या है, 1/r e माइनस दिस थिंग। ओके, और एरिया क्या है, एरिया क्या है, 4πr²। ठीक है, सो ये 4π। ओके, okay, so if you put things together, हमारे पास करंट कितना आ रहा है, 23.1 एम्पियर। इफ यू पुट एवरीथिंग इन दिस इक्वेशन, ओके, तो हमारे पास कितना करंट आ रहा है, 23.1 एम्पियर। ओके, समझ आ रही है बात की, 23.1 amperes,
यस
right?
सर, समझ आ रहा
Now, in second case, in second instance, suppose at same instant, which is t equals to 1 second, t equals to, okay, t equals to 1 second, हमारे पास इलेक्ट्रॉन 6 मीटर का डिस्टेंस कवर कर रहे हैं। ओके, तो करंट कितना होगा, 27.7 एम्पीयर। तो इसका मतलब क्या है कि जब वेलोसिटी बढ़ेगी तो करंट क्या होना है, बढ़ना है। जब इलेक्ट्रॉन्स की वेलोसिटी बढ़ेगी तो करंट ने क्या होना है, ओके, the total current is larger at r equals to 6 than it is r equals to 5। समझ आ रही है? ठीक है,
है।
ऐसा
यस
क्यों हो
सर,
रहा
समझ आ
है, ऐसा क्यों हो रहा है, नेक्स्ट टाइम आपने मुझे इसका जवाब देना है। ठीक है,
रहा है। सर इसकी कोलिजन्स कम हो रही होंगी ना, तो इस वजह से वो डिस्टेंस ज़्यादा ट्रेवल कर रहा है।
हाँ हाँ, ऑफ कोर्स ऑफ कोर्स ऑफ कोर्स, जब हम करंट बढ़ाते हैं तो वेलोसिटी बढ़ती है। ठीक है, समझ आ रही है?
यस, यस सर, समझ आ रही
ओके, सो रिमेंबर, इस केस में हम ये जो आर रेडियली आउटपुट का जो केस है, इसमें हम एरिया एज्यूम करते हैं, ये स्फेरिकल एरिया है। ठीक है, ओके, spherical area, so current is spherical area, right? Current is spherically radiating outward, okay, current is spherically radiating outward, ये just assumption है, just एक assumption है, right? Spherically radiating outward, right? Spherically, okay, this is also like a spherical profile, okay, spherical profile, okay, समझ आ रही है बात की, like the current is moving on a sphere and moving spherically outward, okay. Okay, so coming back to our equation, which is about the conductivity. The conductivity is nqe square tau divided by effective mass, uh, and this can also be termed as Cn is number of electrons, right? And अगर हम इस इक्वेशन से निकालें क्यू ई tau divided by effective mass. इसको हम mobility का नाम दे सकते हैं. So this we consider this as the mobility factor. Okay, mobility. And resistivity is just a reciprocal of conductivity. It will be this value. Okay. Now look. Typically, number of available carriers in metal is very much higher than in insulator. Typically about 10 to the power 22 free carriers in 1 centimeter cube. This is a huge number. Typically scattering time in metal is typical scattering time in metal is 10 to power minus 40 seconds. As I said, sometimes little less, sometimes little more, and it depends on what temperature also. Okay, so the mobility is, so conductivity has a unit of 1 over ohms dot length. Okay, 1 over ohms dot length. So this is what we use for the conductivity, this
हाँ जी,
unit.
बस करें, बहुत है सर आज के लिए.
आज के लिए बहुत है.
यस सर.
So
यस
क्यों
सर बहुत है.
लोग थक गए हो, क्या चक्कर है?
यस सर, थक गए हैं जी.
अच्छा,
सर
लेकिन फिर
इतना कभी ऑनलाइन नहीं पढ़ा है,
हाँ,
आज
लेकिन
बहुत ज्यादा पढ़ा दिया.
लेकिन आपने देखे ये क्या करना है कि इसका आज हमारी 2 क्लासें कंसेक्टिव हुई है ना. पहले
यस
हमारी
सर.
एक एक क्लास होती थी. सो 2 क्लासेस वी हैड कंसेक्टिवली. सो एनीवे, सो इस नेक्स्ट टाइम मैं क्विज अपलोड करूंगा. ओके, सो इसको इसी इसी उससे चैप्टर से होगा. ठीक है, ठीक है.
सर क्या कह रहे हैं? सर एक बार रिपीट कर दें.
मैंने कहा कि नेक्स्ट टाइम विल हैव अ क्विज. ओके, फ्रॉम द सेम चैप्टर.
ओके सर.
अच्छा, मुझे